which is related to the upstream, where we talk about the oil well. There is another scenario in the downstream. Suppose we have a refinery, and refinery is basically refining all the petroleum products and trying to distribute through a plant to the other distribution agencies. So this connection is basically with a pipe, a gas pipe. And we need to understand, like, even though if we have this pipe and the product is refined, even though we have lot of impurities and dust that basically collects, which could be a hydrogen sulfide or liquid sludge, and these are basically collects itself and makes a composite kind of powder, which is called as black powder in this industry. So sometimes when, like, if you don't have a preventive measure of this, so it will block the whole pipeline and it can access the pressure and it can blast. So preventive measure is required. So this solution is basically to provide a preventive measure, like we are passing this much of black powder for this much of duration, and we need to do a preventive, like cleaning of these pipelines regularly. So we need to provide a possible duration based on the amount of black powder is flowing inside a pipeline to the sponsors, where yes, this is the time now you can clean this pipeline, because that cleaning should be optimized, because at that point cleaning it takes a lot of time, and it basically your operation blocks, and that affects your business. So we need to optimize, like how long we need to continue with the same situation, and when it is like a situation we need to clean it up. So we measure this quantity of black powder. So this is the same principle. The solution is provided by the Khalifa University group, where I was the part of this group. So in this configuration, this is a section of a pipeline where a gaseous media and the black powder, which is basically distributed and which is flowing inside the pipeline. Similarly, we are transmitting a signal, RF and microwave signal, at 24 gigahertz here. Earlier, the design was in megahertz. Right now, we are using in gigahertz. So it depends on application to application. So these are two probes which radiates. This probe is radiate microwave radiation at 24 gigahertz, and basically some of the energy is getting reflected back and be measured, and some part of the energy is basically transmitted. So basically, let's assume, like, if you are having a situation where these suspended particles having less concentration, so the amount of reflection and transmission is basically a function of the concentration of these suspended particles inside a pipeline. So we need to measure those suspension, and we need to come up with a solution like this much of black powder is basically flowing inside the pipeline. So this was our solution, and you can see, like, there is some kind of code is written over it. Basically, this is the code which is certified. So this device is basically certified. So you can see this is certified in this lab. This enclosure, this is the stainless steel enclosure, is basically explosive safe. This is a second category instrument. This is to be used in zone 1 for gas, like is intrinsically safe electronics is basically used inside it. There is no battery inside it. So we need to be careful, like these are the very, very critical terms. And suppose whenever you use any device and you develop any device, you need to provide this kind of certification instead, unless you want to use this. So let's come to the sensitivity of this solution. So in this solution, suppose you are flowing a black powder, which is basically a magnetite in greater extent. So in similar, the experiment we have performed in this configuration, we have found the smallest quantity of black powder, which is basically the duration is 2 seconds. So 2 gram, so 0.2 gram per second when transmitted, it gives us this kind of sensing voltage output. This is basically a transmitting through. Similarly, these are various kind of stages. So we can see like this is the very good measurable signal, and this also a very good measurable signal, although this is also, but this is debatable. So we can consider this signal as a measurable signal with this hardware. So this is basically 0.5 grams per 2 seconds. So this, if 0.2 grams of the black powder is flowing inside a pipeline, we can detect through this electronics. So this was our previous achievement. So we have modified this design little bit. Also, this is our industrial prototype, and this is the actual picture where the device is basically installed in the field. And this is the configuration, like the black powder is moving and there is two probes, which is basically in this configuration, we are measuring the transmitted through signal. So similarly, I just also want to clarify like how these things are very important to us. Like we discussed like zone 1 and zone 2 are the hazardous area. So what need to be careful in this domain? The first thing is like this is the pipe. Here we have a pipeline, and this is our device. So device is outside the pipe. So inside pipe there is a flammable substance is basically flowing, explosible substance, and these probes, these are very well much sealed with this. So these are very with sealed probes. So there is no leakage from these points. So we need to very careful about the sealing and everything. So the thing is, once we have sealed this, so this is comes out of zone 1. So this instrument is being used in zone 1. So that's how it is certified for zone 1 only. Okay. So however, these probes and this shielding mechanism should be like in zone 0. So they should be like they should be in a situation to avoid any calamity. Similarly, so these two probes is basically connected, and here we have well matched shielding here, because we don't want any leakage to occur on these points. So we have this transmission and RX. So this is zone 1, although there is a debate on zone 1 and zone 2. So while doing this experiment, our the certified agencies tells us like you have to keep all the electronics 50 meters away from this box. So we have all the electronics, all the instrumentation, which is 50 meters away from this. So this is the hazardous zone, which is basically depends on the like industry to industry. So this was like in this. So they have kept us about a 50-meter distance. So this meeting this requirement of 50 meter, it's very critical for us, because the signals get dying out with this. These are the very low quantity amount of signals, and we didn't have any kind of battery in it. We need to drive this circuit from the power source of 50 meters away. So these are the critical requirements that we need to come up with, and we need to be very careful about these. So let's come to the enhancement in the previous work. So earlier our probe was like a circular probe, basically a circular waveguide, which is basically filled with a Teflon, very tight Teflon fitting. And this is basically a non-resonating structure. So what we think, like if we replace or if we like attach a resonant iris on the top of it, it somehow increases the electric field intensity near to the probe. So we have also identified while doing the numerical simulation, like up to the 10 mm, the electric field intensity of this probe is greatly improved, although the electric field intensity after 10 mm is almost identical with this. But this is a big achievement, because if we have, which is very near to this this distance, which is a 10 mm, which is a great standout distance, then we can have a very high electric field around this iris. So this iris, we can see like this was the probe which we were using, but we have placed the iris over it. And the iris dimension is basically, we need to cut out this kind of shape out of it. So this structure basically resonates at one frequency. So we designed this probe at X band. So it depends. So we have designed, because it was difficult to be designed at 24 gigahertz. So we designed at lower frequency for the validation purpose. So we need very specialized, because these dimensions getting smaller at 24 gigahertz. So we have designed it 8 gigahertz. So this is the concept validation. So we have started with this. So once we placed our iris over it, so we have found that the probe basically resonated one frequency. So this is the rate and loss characteristic of this probe. And we also found that the dimensions of this probe is like, we have optimized these dimensions, and we have started with the lambda by 4 assumptions and something like that. And we have also found that if we want to like shift this resonance frequency with these parameters, we have also done the parametric analysis by which we can like decide like the width and gap and the radius to resonate this sensor to at a particular frequency. Maybe we can design it per 9.5 also. So maybe we can design it per 10 gigahertz also. It depends greatly on these parameters. So then we have provided a coaxial feed to this, and we have performed the simulation after incorporating. Earlier we were using only the kind of waveguide probe, and then we have a proper feeding of coaxial like coaxial line, and then we simulated the design. So this improves the performance, and these are some parameters of it. Now this is very important aspect, which is the sensitivity analysis. So what we were doing, we are attaching these two probes in earlier cases to the main like fluid propagating line. So we have modeled equivalent electromagnetic model in the CST, or you can design in any of the software, electromagnetic software. So what are the things, like we need to have this cylinder, and there is a filling media inside it, and the properties of that media, basically some sort of the variation in those properties with some sort of relation of the actual situation. So what we considered, we basically mix two substances. The one is like, there are in natural gas and black powder, we have two common, like black powder, which is basically in most of the cases, which is magnetite, and we have a gas, which is methane. So what we did, we have to come up with a mixing model, which is like, if we mix these two substances, what would be the effective permittivity. So a lot of like mathematical modeling inside involved here, and then what we have done, we have come up with a volumetric concentration of magnetite inside a methane. Or methane is basically having a property which is relatively almost equivalent to the air. So permittivity of the methane is basically can be considered as a 1. So what we did, we mixed these two kind of substance, and we get what would be the, like if we change the volumetric concentration of one of the constituent, what would be the change in the permittivity and permeability of the media. Sorry, in this case, we have not considered the magnetic case, so it's only the permittivity and the loss. So what we found in this analysis, so when we change the properties of the flowing media inside it, we have found the magnitude of S11 and S21 is changed with the volumetric concentration. So this is the volumetric concentration. So at lower kind of volumetric concentration, both S11 and S21 follows a nature. Then later on we found like S11 is not responding enough, although the transmission is responding, and transmission is getting reduced because the most of the energy is getting reflected back. Similarly, in case of phase, we have found that phase of S11 and phase of S21 almost responding to this distance, like 0.15% of magnetite in a mixture of air and magnetite. So they almost shows a similar kind of behavior. Then and later stage, like S21 becomes a slightly more sensitive to the variations. What we found, like for this change in the resonance frequency, which is very interesting here, like these parameters are changing very less in this region, but this parameter is start changing in a great extent, like 100 megahertz, 200 megahertz, 300 megahertz, while changing in very small amount. So this is the very interesting aspect, because our sensor is now resonant sensor, and we are utilizing the property, and the electric field is basically focused near to the region where we place the iris. So we have done some sort of measurement over it. So in order to perform a measurement for this kind of scenario, so we need to like emulate the complete environment. The complete environment is like something like air is mixed with some sort of sand, and which is uniformly flowing inside a pipe with a right amount of dispersed media. So we need to place a lot of sensors in this. This is also called as a calibration rig. So here what we provide like the air supply from the compressor, and this is the air booster which takes some air from the environment, and it creates a very like a flow of air, which is like a laminar flow of air. Then what we do here, these are various other sensors. This is called pitot tube, which is basically which basically measures the velocity of air and everything, and which also measures the temperature. Similarly, we have this as feeder, where we are feeding a sand in this to have a mixture of air and sand to emulate the conditions like we are in a similar scenario like gas and black powder. So right now we are considering air and a sand, very fine sand. So it get well mixed and it is flowing. This is our microwave section, where we have placed two probes, the design probes, and the mixture is basically flowing inside this pipeline. And later on we are like increasing the cross section of the pipe, because we want to reduce the velocity of the like this mixture, so that the suspended particles of like sand, it easily get settled down in this bag. And there is an air filter. The excess amount of air basically being it's basically filter from this filter, and all the sand which is basically being fed by this feeder basically collected at this bag. So this is the overall experiment setup. So what we did, what we did here, like we have a control section here. So we decide which flow rate to be like maintained, like how much like the sand to be inserted in this. So we have a program software. So we can feed a small amount of the sand in this pipe based on the program. Similarly, we can have a connection of this a LAN connection between this VNA and this computer. So we can remotely measure the S parameter resonance frequency according to our convenience. So what is the outcome of this overall analysis? The thing is, like earlier, we were in situation like we have the sensitivity of 0.2 grams per second, but by using this configuration, by employing a resonant kind of a structure over the tip of the probe, we have increased the sensitivity of 55 milligram per second. So here are the results where we can clearly see, like this is the reference, that means there is no sand present, only air is flowing inside the media. So this is the response of the reflection coefficient. Similarly, if we have 55 milligrams, then we have another signature. So there is a slight difference, and there is a slight difference in the resonance frequency as well. If we can see, if we can draw a line at the individual minima, then there is a shift. We can easily identify this shift in the resonance frequency. So with the using of this setup, we have increased the sensitivity a lot. Similarly, these can also be seen in the terms of phase. So we have measured the phase at 3 different instances where the flow was basically the sand was fed at 55 milligram per second and 3 milligram per second. So this was another example. So now I'm trying to summarize the whole lecture